Chapter 10, we're continuing on to ellipses. So what we're going to be doing, the section in this textbook starts right away with a discussion on what an ellipse is. I don't remember in the actual textbook itself if it goes over the derivation of the formula for an ellipse. It's a pretty lengthy derivation if you've obviously never done it before. So the notes that I use for these videos and for the lectures in class don't have any room for the derivation for this formula from what I remember. So what I'm doing is I'm going to go ahead and have the separate video for just the derivation for ellipses. We're going to do another one for hyperbolas because I believe it's the same situation for 10.3 for hyperbolas where there's no derivation and no room for derivation. So I'll have a separate video just for the derivation. It should be a short one. And then we'll have another video that'll follow this one shortly over a couple of practice problems, practicing the characteristics of ellipses, and given characteristics of ellipses, find the equation of that particular ellipse and so on. So we'll continue on to we'll start with the definition. The definition of an ellipse, this is the loci definition in geometry, and we can boil it down literally to 2 points. So an ellipse is actually the set of all points on the plane, the rectangular plane, which have some sort of relation to 2 fixed points on the plane. Those 2 fixed points are going to be called focal points. So what we do is, let me draw it here. So with the way that the ellipse is drawn here already, so I've already drawn the ellipse, and I'm already kind of suggesting what we're trying to prove is true. So what we're really just trying to do is derive the formula for that curve that's given there. It ends up happening that if we solve this particular loci geometrical equation, then you get that blue curve, that ellipse. So there are 2 points. We'll place them somewhere. We have a coordinate grid posited, and what we'll do is we will go ahead and on the x-axis draw 2 different x coordinates. They have the same value, but one's negative of the other. So we'll call that value C, and C this way. And that'll be negative C that way. So that way this point back over here, or the point in the front, is 0, comma, or not 0, comma C, C, comma 0. And then this point back over here is negative C, comma 0. So that way the distance between the point that's there on the x-axis and the origin is C, same as this point and the origin. So that distance from that one point on the x-axis to the origin is going to be C, and it's going to be the same on both sides. So those are my 2 focal points. We can call that F1 and F2, or I can call that F and I can call that G, because I don't want to use subscripts for like 1 and 2 for the same letter. So that gets more confusing when you're using subscripts like that. So F and we'll say G. Okay, so the relationship between those 2 focal points and any other point on this ellipse or on this curve, assuming it's not an ellipse yet, so it's some curve out in space or some curve out on the coordinate plane, what we do is we measure 2 distances, and I should have labeled that as a point. So we can call that point P. So I'll give a letter to it, and what we do is we take distances between that point P, and it's any point, and I just drew a random point on the ellipse, any point on the ellipse. And we're going to draw a straight line segment from that point to either of those 2 points, or to both of those 2 points. So there's going to be distances between those 2 points, which correspond to lengths of those segments, FP and GP. So those 2 distances, the way that we define an ellipse is that those 2 distances, when we add them up, will end up resulting in the same value no matter where we're at. So if I actually draw P back down over here, a little further back down this way, so if we move that point P down here, then if I take those 2 distances and draw 2 new line segments this way, then if I add those 2 distances together, so we can call those D1 and D2, and I just broke my own rule. I said I wasn't going to do subscript for, well, in this case for points. This would be D2 over here. So D1 and D2 for that first, or that initial placement for that point P, when you add those 2 distances together, it's the same as if I had added these 2 distances together for that second placement of that point P. And that's actually true for all points along the curve. That would be true for all points along the curve. So I'm going to try to erase this one here, the second one. So I'll just leave the initial. So just take that as an arbitrary point P along the curve. So what's true for any point on that curve is if I take the distance between F and P and then G and P, add those two distances together, their numbers, add those two numbers together, I get the same value no matter where I place that point P. Okay, so where to even begin deriving the formula for this thing? So what we do is we consider special points along that curve. So we're going to go ahead and assume that it's a curve, a nice one connected curve, just a single loop. And that's actually what it is. What we're just trying to concentrate on here, we're not trying to do anything too rigorous. We're just trying to figure out what the formula should be that relate the x and y coordinates to each other. So we'll start off specifically with the x and y axes by themselves. So we're going to consider special cases. And I'm going to consider my first special case, so that way there is a point on the y-axis. So we're going to assume, and the curve of course suggests it, we're going to assume there is a point on the y-axis. In this case we see 2. There is a point on the y-axis that satisfies that property if we set a specific value for that distance k, or for that distance, which is the sum of those two, and we normally use the letter k for that. So there's going to be this point here. We will call, or I'll go ahead and give coordinates. That's going to be 0, comma, and how far off do I want this to be? We usually use the letter B this way. So I've already used the letter C, and there's a reason why. There's a specific order when we use these derivations. Now earlier we used A and B for vertical and horizontal components, not respectively, so not in that particular order. But we used A and B for horizontal and vertical components of vectors, or the first and second coordinates of ordered pairs earlier in the previous sections for chapter 8. So we'll be going with the same convention. B is vertical, A is horizontal, C is just some extra number that I started off with actually. So then we start off with B, and we're going to say that that's B, therefore this is the point 0B. So there is some point up there on the positive y-axis that satisfies this, this property. So we're going to call, let's see, how would that get done? You would draw two line segments, one from that point to F and one from the same point to G. So then what we do is we find those two distances. I'm going to call this little d1 and then little d2. So lowercase d1 and lowercase d2. So the lowercase will denote a distance in this case, or a lowercase d denotes a distance. So it's 1 and 2. So then I'd like to find out what the expression is for that total distance there. Now, first off, it doesn't matter where we're at on the parabola, the ellipse. I could be here, and it's going to be the same distance added together for those 2 points, or for those two, to those 2 points. So d1 plus d2 is my beginning formula. That's going to equal to, and it's the same, it's constant, so it says here somewhere, is constant. So the combined distances for those two fixed points is going to be constant. So d1 plus d2 is going to be some constant. I've already used a, b, and c, or I'm planning on using a, b, and c. So I'm going to go ahead and use a different letter, and I'll just call that k. That's I think what the textbook calls it. So initially we'll call it k. So let's find out what those actual distances are. So we have a setup here where I can probably use right triangles. Trigonometry is a very, very useful trick when deriving formulas. You break things down in terms of rectangular coordinates, or two perpendicular dimensions forming a rectangular grid, and you can do a bunch of right triangle trigonometry to simplify some stuff out. So I see two right triangles. I don't know if you do. So this one here, that's a leg for one of the right triangles. This is another leg for the same right triangle, and this is 90 degrees since we're talking about that being a line segment that's a piece of the x and the y axis. So those x and y axes are perpendicular to each other. So then I could find out what the value of d1 is and d2 are by knowing what these leg lengths are. So first off, if I look at the one on the left, since we're talking about d1 first, this is a distance of c from here to here. That's a distance of c from there to there. Now let's talk about the other leg distance, or the other leg measurement, side measurement. That's going to be b, since that's b from here to here. So hopefully it's obvious to you. I hope so. D squared is equal to b squared plus c squared, or d1 squared. So d1 squared is b squared plus c squared. Because we have a right triangle, d1 is the hypotenuse of that right triangle. B and c are the measures of the side lengths of, or the legs of that right triangle. So therefore, and traditionally it's a squared plus b squared is equal to c squared, but it's leg squared plus other leg squared is equal to hypotenuse squared, and that's how we form that. So d1 squared is equal to b squared plus c squared. However, you can also see that the other triangle is actually congruent to this one. We have another right triangle with a side length c and another side length b. Hypotenuse is different, but in this case we have an angle or a side angle side in this case, so they're actually congruent to each other. So we also get that d2 squared is equal to b squared plus c squared, since d2 is the hypotenuse of the same triangle. So d1 and d2 actually end up having to be, or they end up being equal to each other. So k ends up equaling to 2 times the square root of these two quantities. So if d1 squared is equal to b squared plus c squared, then d1 is equal to the square root of b squared plus c squared. Therefore, k is equal to 2 times the square root of b squared plus c squared. That's our first fact. So fact number 1 for ellipses. So if I go ahead and call the focal distance c, or if I label the focal distance c, and if I label the vertical distance, the halfway vertically, b, then that number k, where the combined distance between that point and the other two focal points is constant, that constant k is equal to twice the square root of the sum of the squares of those two dimensions c and b. So that's our first major fact. And I'm going to go ahead and erase a lot of this because I'm going to be using the same picture for derivation. So that was the special case where we were on the y-axis. Same is going to end up being true on this other side of the y-axis, but I don't have to go through that. And it's not going to be useful to look at that situation again. We're still going to end up getting that k is equal to 2 times the square root of b squared. 2 times the square root of b squared plus c squared. So I'll go ahead and erase all this, well, the majority of it. I'm going to leave those two focal points for sure. Oops, and I meant to leave the entire focal point. I didn't. Okay. So F and G are my two focal points, or my two foci. That's plural for focus. So those are my two foci. Okay. So let's consider another special case, and this one's a little weirder to consider. Let's consider a point P on the x-axis. Let's say the positive x-axis. It'll be the same for the negative side of the x-axis. So P was up here, and that's what gave us this first fact. And I'm going to try to extract some more information by moving that point, not F, it was P. That point P is now moved down over here. This is my new location for the point P. What new info can I extract by placing P there? So again, it's true that those two distances, D1 plus D2, is equal to K, which in this case is 2 times the square root of A squared, or B squared plus C squared. So that's still true. And let's see, I used red to connect those dots. So what are those two line segments that we drew earlier? It was connecting F to P, which I'm going to draw it curved, and that's not supposed to be curved. It's supposed to be a straight line. And then G to P, and I'll draw that one curved too. So I'm supposed to take these two line segments and add their distances, or those two lengths, and that's still supposed to equal to K. So again, this is D1, distance number 1. This one right here is distance number 2. I wrote 1. So that one's distance number 2. So the next fact, well, not really a new bit of information just yet. D1 plus D2 is still supposed to equal to K, which in this case we know K is equal to 2 square root B squared plus C squared now, which is a major bit of information. So what we're going to do is we're going to come up for an expression for D1 and D2, which is basically how we found this bit of information for that first special case. We found out what the special value of D1 plus D2 was for that situation. Then we're going to redo it for this situation, see if we can boil this down to some simpler numbers or a simpler expression. So what's D1 and D2 in this case? So in this case, it's not really that tough to see. How do I find out how long those segments are? So from here to here is D1. So this big length here, that's D1. So how much is that? So I notice that that's C from here to here, C from here to here, And where's that? Right here. And then there's this little extra bit here, which I kind of got a little ahead of myself. I'm missing a number here. So earlier when we did this for the vertical portion, we came up with a number that represents the value where that top portion intersects the y-axis. We got to do the same for the x-axis. So we called that value up on the top b. I'm going to call this value here a. So that's a comma 0. And back here, this other vertex is negative a comma 0. So what would that make this little distance here that's missing on the side? What would that make this thing? How long is that side length? So that is, well, a is a bigger number, c is a smaller number, or a is bigger than c, c is smaller than a. So to find out what the distance is between them, you take a and subtract c, so that's a minus c. So all three of those added together, d1 is going to equal to c plus a minus c. That right there is d1. So all of this together is d1. d2. What is the value of d2? The value of d2 is the same little sliver here that is measured by a minus c. So that's supposed to be plus a minus c. And that's supposed to equal to 2 square root b squared plus c squared. So then what we do, and actually I forgot to label this one is d2. So that's d1 plus d2 is equal to that, which was supposed to be the value of k earlier. So then what do I do with this? We simplify the left-hand side, see what we get. So that's 2c. c plus c is 2c, plus, that's going to be 2a minus 2c if you do that correctly. You can drop parentheses on both of those. The a's combine to 2a. The negative c's combine to negative 2c. We could cancel out these two c's, and we're left with 2a is equal to 2 square root b squared plus c squared. So then I could simplify that. 2a is equal to 2 times this quantity. It must be the case that a equals to the square root quantity, square root b squared plus c squared, which I could manipulate that a little bit more. You can square both sides. If that's the case, a squared is equal to b squared plus c squared. So what I could also do is I can solve for c squared. C squared is equal to a squared minus b squared, which I'm going to go ahead and box that because that's a very, very important fact. That's how we find the focal distance, c, if I know the sizes of those axes, the major axis and the minor axis. So ellipses, unlike parabolas, have two axes of symmetry. So they are both vertically and horizontally symmetric. So there's a horizontal axis of symmetry, we call it the major axis, and then there's a vertical axis of symmetry, we call it the minor axis. So if I know how long those axes are, you divide them by 2, because it's 2 across. It's a above, a below, or sorry, a to the left, a to the right, b above, b below. So we divide those numbers by 2, and then we plug them into this formula. That's going to give us the distance away from the center of that thing to the focal points. So there's our formula for the focal distance. So this is our focus or foci formula. So that's a very, very important formula. That's one you need for your notes, especially when you're solving these practice problems. Okay, so that's very, very important information. So we're still missing an expression with x's and y's in them. So then what we're missing here, what we got to do to take it to the next level, is to consider a point that's not one of these two special cases. So the special case at the beginning was where we were on the y-axis. We just finished considering the case where we're on the x-axis. Let's get off axis. So if I completely move that point P somewhere else off of an axis, some arbitrary value. So let's say P is here. And that point P, since those are going to be arbitrary x and y coordinates, and I could have drawn it anywhere I want, I just happen to draw it in the second quadrant. I can draw it in any of the other 3 quadrants if I wanted. We have variable coordinates x and y. And what we're doing is we're still taking the distance d1 and d2 between P and F and P and G. let's see how that works out. And if you already know that you're going to have to plug into distance formulas, then that's what we're going to end up having to do. So distance formula twice for these. And this is where it gets a little ugly. So the algebra gets a little complicated, but hopefully you'll be able to follow. So we had two distances, d1, d2. d1 is the distance between points F and P. And there's a formula for that. It's a square root, and it's going to be the sum of the squares of the differences between corresponding coordinates. So you take the differences in x coordinates. So let's take this one to be point number 2, and this one to be point number 1. Then it's going to be x minus negative c. So it's going to be x plus c squared. You do the same thing for the y coordinates. So it's going to be y minus 0, so it's plus y squared, square root. We're going to add to that little d2, which is the distance between P and G, or G and P, doesn't matter what order, it's the same thing. It's going to be plus because we're going to add it. And this distance is going to be the square root. So square root of the sum of the squares of the difference in corresponding coordinates. So you look at the difference in x coordinates. That's x minus c. We square that difference. We add it to the sum, or we add it to the square of the difference in y coordinates, y minus 0. So I don't need parentheses for that one, y squared. And what happens when I add these two quantities together? When I add those two quantities together, I get k. Now we have a simpler formula for what k is. K is equal to, let's see, square root of a squared plus b squared. And we said that a squared is b squared plus c squared. So it looks like it's, well, in this case it was what? 2 times the square root quantity, b squared plus c squared. But we just found out that a is equal to square root of b squared plus c squared. So the simplest way that I can write this is 2a. So that's another thing I could have written. K is equal to 2a. Here's my formula. It's not complete yet. It's got a bunch of square roots, and we're not going to want any of those square roots. So the next task is to get rid of both of those square roots. This is the ugliest part of the derivation. Hopefully you can follow. So I'd like to get rid of those two square roots. And we've done this before at the beginning of the year, back in chapter 1, where we went over various methods for solving equations. So there were equations involving roots, not just square roots, cube roots, and stuff like that. And the way that we got rid of those roots in an equation was to apply a power operation to both sides of the equation, simplify that version of the equation, or simplify that equation, solve it, and then we check the solutions of the equation that we raised a power to, and then we plugged them into the original to check the solutions that way. So we're going to do something similar here. In this case, since we have square roots, we're going to square both sides. Now, I'm not going to square both sides the way it is. You have a choice. You can square both sides the way it is. I don't like working with the square root, two different square roots on the same side. Me, personally, I prefer to work with one square root on one side and another square root on the other. So that way I can actually get rid of one of the square roots at a time. So there's really no advantage over the other. It's just kind of a personal preference that I have, and it's something I like to do. So what I'm going to do is move one of them. I'll keep the one on the left. So square root x plus c squared plus y squared equals, that's going to be 2a, and then minus the other one, square root x minus c squared plus y squared. So all I've done is I've taken one of those square roots and I've moved it to the other side. So I haven't really squared anything just yet, so now that's what I plan on doing. So we're going to square both sides. So I'll go ahead and do it in a different color so we can keep track of all the operations that we were doing. So square, and then square. On the left, the whole idea behind isolating one of those square roots is when I square both sides, that square root goes away completely. This was the whole point behind moving one of them. So now I have no square root on this side. I'm going to have to deal with the right-hand side, though, which is a binomial squared, which contains a square root in it, and we're not going to completely have eliminated the square root on the right side. That's okay. What I'll do is I'll clean this up. We'll expand this to what it actually ends up becoming in its full form. We clean it up. We isolate that square root term again, and my strategy right now is to isolate that and then square both sides a second time. And hopefully, I'm planning, those square root quantities will be gone after that second application of a square. So first, the expansion portion. So how do I expand that? That's a binomial squared. A binomial squared comes out as a perfect square trinomial. You take the first term, 2a, and you square it, 4a squared. You take the two individual terms, signs included, you multiply them, and then you double the result. So that's going to be minus 4a square root x minus c squared plus y squared. And the reason being, if I take alpha plus beta and I square it, you get alpha squared plus 2 alpha beta, and then plus beta squared. So I kind of ran out of space there. But that's the perfect square formula that I just applied. And I'm not even finished applying it yet. That's the middle term. That's the justification for the middle term. So the third term is where you square the second term inside the square. So it's going to be plus, and I'm squaring a square rooted quantity, so it's only the stuff inside of the square root. So x minus c squared plus y squared. And that's what that looks like, completely expanded out. And a shortcut, basically. So the non-shortcut is to multiply that binomial with itself, do FOIL, and you have 4 terms. The two middle terms will combine. Okay, so is there anything I can do? There might be some stuff I can do. I think I can go ahead and expand those x plus c squared terms and x minus c squared terms on either side. I'm talking about this right here. So I think I can do something with that. I already know that if I expand that, it's going to be another perfect square trinomial, and it's going to be very similar to this other one on this side. They're not the same, identical, so they're not identically the same, but they're going to contain a lot of common terms that we can end up canceling out by subtraction. So that x plus c squared is x squared plus 2cx plus c squared. That's supposed to equal, or actually no, plus, there's a y squared that needs to get dropped down, equals to 4a squared minus 4a square root x minus c squared plus y squared stuck inside of a square root, plus this one becomes x squared minus 2cx plus c squared plus y squared. And that's what that looks like, fully expanded out. I could also expand the inner x minus c squared term inside that square root, but no, I'm not going to even bother just yet. I'll do that later. So way later. So what do I see? Now that everything's completely expanded out, it should be a lot easier for me to cancel stuff out. Notice there's an x squared term on both sides. Those are going to cancel. There's a c squared term on both sides. There's a y squared term on both sides. So a bunch of stuff cancels out. And let's see what I have left over after all that cancellation. That is 2cx equals, so that's the only thing that survives on the left-hand side, 4a squared minus 4a square root x minus c squared plus y squared, and then minus 2cx. So what I see at this point is it's going to be a little easier for me to isolate that square root term. I want that square root term by itself, and I'm going to repeat the process that we applied here. So in that situation, we had two square roots. We isolated one of those square roots, squared both sides. We eliminated that square root, and we're only left with the other one. So that other one is now the one that I plan on moving or isolating, and then squaring both sides again is going to be the game plan. So because that has a negative sign in front of it, that's the term I'm probably going to want to move, and everything else is going to get moved together to the opposite side of the equation. So that negative 4a square root term is going to get moved to the left-hand side instead. So negative 4a square root x minus c squared plus y squared is now a positive on the left-hand side. And I'm going to go ahead and move everything else to the right-hand side. The only thing I need to move is that positive 2cx. It's going to get subtracted. It's a negative 2cx. You're left with 4a squared, and that negative 2cx combines with the other negative 2cx. They don't cancel, they double. Negative 4cx. And that's what I have now. So I'm going to erase that plus sign to that positive sign. You'll notice everything's divisible by 4. So what I'm going to end up doing to isolate that square root, I'm going to divide everything by 4a. So this little 4a, I'm going to divide it out on this side. Those will cancel. And in order to balance this equation out, I must also divide by 4a. Now that I'm introducing division into this procedure, I need to be careful. I can't always just divide with impunity. I need to check, is there any variables in what I'm dividing? And the answer is yes, I have a variable a. So this variable quantity a corresponds to the length of a segment that is formed by taking the origin, O, and then this point P up here. That length is positive A. The value of A is positive. Now I don't care if it's positive or negative. All I care about is it not being 0. A is not 0. If A were 0, I no longer have an ellipse. So I think we're okay to divide by that value A because it's a non-zero quantity. So if that's the case, I'll go ahead and erase this stuff, and I'll treat it as if I had already had it with a 4a on the bottom. So this is what I currently have. And I want to box it, but that's not my final answer. This is nowhere near what we're supposed to have just yet. I'm trying to look out here to the side for some extra space. I kind of made this a one-pager, thinking I was going to be okay with the space that I had out here. So what I'm going to do is I'm just going to continue it down here. I guess that's fine. So we have square root x minus c squared plus y squared, square root of the whole thing, equals to 4a squared minus 4cx over 4a. And what I'd like to do to get rid of that square root is we're going to square both sides, and we're almost going to be done. So if I square both sides, I get x minus c squared plus y squared is equal to, and I got to square that entire side. Well, here's the thing. All of this stuff can get divided by 4 for sure. And I could also maybe distribute the a in there too. So let's see if you're okay with this. This is going to be a, and then minus cx over a. That's what this thing becomes. You divide 4a squared by 4a, you get a. You divide negative 4cx by 4a, and you get negative cx over a. Only the 4's cancel out in that situation. So what I'm doing here is I'm squaring a minus c x over a. That's the quantity that I want to square. So I think I need to be a bit more, actually no, I'm going to leave it as a c for now. I notice that there's a c in there, and c can be related to a and b, but I'm going to worry about that later. So I'm going to leave the c in there for now. Maybe worry about that at the way end. So then what I have to do now is I might want to square everything. So expand all of these square terms. So x minus c squared, we already know that one. That one's x squared minus 2cx plus c squared plus y squared gets dropped down is equal to, well, if I square this binomial, same idea, a squared minus 2 times the product of those, which is going to be cx. The a and the 1 over a, or the a and the division by a are going to cancel each other out. A is non-zero, they cancel. And then we're going to get plus c squared x squared. So let me make that a more noticeable, c squared over a squared. That's what happens when we expand that right-hand side term. Okay, so is there anything that we can do? Is there anything that I could do here? And I think so. We can cancel out the minus 2cx terms. That's nice to be able to cancel those out. X squared. And maybe what I could do is I can go ahead and move this over to that side since it has an x squared on it. And I can combine those two. So that's x squared. That's going to be a minus c squared over a x squared, which I'm going to go ahead and move that x squared outside of the fraction. That's perfectly fine. Let me rewrite it. C squared over a x squared. I have that extra c squared there. That nothing happened to that, so that's plus c squared. I'm going to end up moving that. Plus y squared equals to, in this case, that's a squared minus c squared. So what I did was I took this guy and I moved it to the right. I left this guy there. I left the y squared right where it's at, and that should be good. And we moved this one over to this side. Yeah, so that's what was done. So far, we're almost there. X squared minus c squared over a x squared plus y squared is equal to a squared minus c squared. So let's see here. I'm going to go ahead and combine these two x squared terms, and you're going to end up getting, if you do this right, oh, let's see here. I think I did something wrong. You probably already noticed that I did this wrong. I forgot the square on that a on the bottom. So that kind of threw me off a little bit, so I noticed that something was wrong there. I was expecting a square on the bottom. So that makes it a lot better. So I got to combine these two. And those two, when I combine them, you get a squared minus c squared over a squared as a coefficient in front of x squared. So here's the reason why. I'm going to write those over to the side. X squared is 1x squared minus c squared over a squared. I got to write that 1 as an a squared over a squared to be able to combine those two. So then what you do is you combine a squared over a squared and negative c squared over a squared by subtracting the numerators, a squared minus c squared over a squared. That's where we got this over here. Plus y squared is equal to a squared minus c squared. Oops, and I put b squared. C squared. It's because I kind of have the Pythagorean theorem in my mind and I want to write out a squared and b squared together. So it's a squared minus c squared. That's actually not a bad thought because there's a relationship between a squared, b squared, and c squared. What was the relationship? Somewhere up here. I boxed it here somewhere. C squared is a squared minus b squared, or a squared is b squared plus c squared. Let me write that one down. A squared is b squared plus c squared. Actually, no, maybe not that one. C squared was a squared minus b squared. Is that what it was? Yeah. I'm going to keep this in terms of a and b because I choose to. So that was a squared minus b squared. And I'm going to try to eliminate c from this equation. So the way to do that, oh, you might notice something already. So there might be an easy way to do this. If I add b squared both sides, and if I subtract c squared both sides, you end up getting b squared is equal to a squared minus c squared. So minus c squared over here minus b squared over here. So if you subtract b squared, or if you subtract c squared both sides and add b squared both sides, you get b squared is equal to a squared plus c squared. This ends up becoming b squared over a squared, x squared, plus y squared equals b squared. And we're almost there. One final step. And what we're going to do in this case is we're going to divide both sides by b squared. So if I divide both sides by b squared, I get x squared divided by a squared plus y squared divided by b squared. And then that equals to 1. And the same argument that I made for a being okay for me to divide by, we can divide by b squared because b is also positive. B is a positive quantity because that represents the number or the location at which that ellipse intersects the y-axis or coincides with the y-axis. Here's my equation. X squared over a squared plus y squared over b squared is equal to 1. So this is the standard form for the equation of the ellipse, and it's going to be centered at the origin. So the very, very center is the origin 0, 0 in this situation. Now if I wanted that to be off center, or if I wanted that to be off the origin, then you would use the same geometrical or algebraic transformation for that geometrical shift. So it's x minus h quantity squared over a squared plus y squared over, actually not y squared, y minus k squared over b squared is equal to 1. And this is our standard form for the equation of a ellipse with any vertex, where the vertex coordinates are h comma k. And that'll be it for this video.